The fundamental laws that govern the universe speak to us only in the language of mathematics. The key to understanding this language is calculus. Calculus allows us to see the true beauty of nature. Calculus makes the predictions of modern physics possible. The variable y represents distance in space. The variable x represents moments in time. The purple line represents the relationship between space and time. This line shows what the distance in space is for every moment in time. Let us focus on what happens during just one unit of time. The distance traveled in one unit of time is what we call speed. The speed is represented by the green rectangles. Suppose we add the areas of all the rectangles together. The areas of all these rectangles add up to the distance traveled. Now let us consider a different scenario. Again, consider what happens during one unit of time. Again, the speed is the distance traveled in one unit of time. As before, let's add all the rectangles together. As before, the areas add up to the distance traveled. Up till now, we have only been dealing with cases where objects move without changing speed. Now let's consider a case where we change speed and sometimes move backwards. Again, the speed can be represented by a group of rectangles. This graph shows that the speed is no longer constant. Every moment in time now consists of a different speed. A negative speed is represented by yellow rectangles. A negative speed means that the object is moving backwards. Let us once again add the areas of all the rectangles together. The yellow rectangles have a negative area and cancel out the green rectangles. The area that is left once again represents the distance traveled. Let us change the graph for the speed of the object. Before, the graph of distance versus time consisted of sharp corners. Now the graph of time versus distance is much smoother. Now the graph is a smooth, continuous curve. Let us once again add all the rectangles together. No matter what kind of graph we have, the rectangles will always add up to the distance traveled. This is the fundamental theorem of calculus. Consider a very small increment of time, which we will call dx. Consider the distance traveled during this time, which we will call dy. The speed is the distance traveled divided by the time taken, which is dy divided by dx. We can therefore relabel the speed as dy divided by dx, and we refer to it as the derivative of y with respect to x. If we extend this white line, then dy divided by dx will be the line's slope. For every moment of time, dy divided by dx is the slope of the extended white line. As the slope increases, dy divided by dx increases. When the white line is horizontal, the slope is 0. When the object moves backwards, the slope is negative. Let us again consider the situation where we had large step increases in speed. The purple line will now no longer be smooth and will again have sharp corners. Each time we pass a sharp corner, the slope changes abruptly, and this is why dy divided by dx changes abruptly. Now let us return to the case where the speed changes smoothly. Let us give a new name to dy divided by dx. Let us call it f of x. For every value of x, we have a corresponding value of f of x. For the yellow rectangles, f of x is negative. The distance traveled during a very small amount of time is the speed multiplied by the time, which is dy divided by dx multiplied by dx. Since dy divided by dx is called f of x, another way to write down the distance traveled during this moment of time is f of x multiplied by dx. This equation, f of x multiplied by dx, also happens to be the area of the rectangle representing what happens during this moment of time. The area of the rectangle is length multiplied by width, which is f of x multiplied by dx. Therefore, the area of this rectangle is exactly equal to the distance traveled during this moment in time. The area of the entire graph is the sum of all the individual rectangles. Therefore, the area of the entire graph is the sum of all the different values of f of x multiplied by dx. We use this symbol to indicate the sum of all the different values of f of x multiplied by dx. We call this the integral of f of x. The integral of f of x represents the area of the entire graph, with the yellow rectangles having negative area. In this case, we are interested in the area of the graph between the time where x is 0 and the time where x is 10. We represent it like this, and we call this the integral of f of x from 0 to 10. The integral of the graph of the speed will always be equal to the distance traveled. This is the fundamental theorem of calculus. This is the foundation allowing us to write equations describing how all objects in the universe behave. This is the language in which the fundamental laws of the universe are written in.